In this module, you will learn about heat engines and refrigerators. We know that mechanical energy is required to run many machines. But major sources of energy, like fossil fuels, can generate heat energy. A device that converts heat energy into mechanical energy is called a heat engine. A steam engine, diesel engine, and a petrol engine are some examples of heat engines. In any heat engine, a small quantity of matter, usually called the working substance, acts as the system. For example, water is the working substance in the case of a steam engine. And a mixture of fuel and air is the working substance in the case of a petrol engine. The working substance undergoes a sequence of processes that finally leave it in the same state in which it started. Such a process is called a cyclic process. The schematic representation of a heat engine is as shown. In each cycle, the working substance passes through the following main processes. First, it absorbs heat from a hot reservoir maintained at a high temperature. Let the temperature of the hot reservoir be T1 and the heat absorbed by the system be Q1. After absorbing heat from the hot reservoir, the working substance does some work on the surroundings and converts part of the heat absorbed into mechanical energy. Let the work done by the system be W. At the end, the working substance rejects some heat to a cold reservoir, maintained at a low temperature, say T2. Let the heat rejected to the cold reservoir be Q2. Again, the working substance goes through the same cycle. To get the required mechanical energy, the working substance goes through the same cycle repeatedly. In a cyclic process, the initial and final states of the system are the same, and hence there will be no change in its internal energy. That means delta U is equal to 0. But according to the first law of thermodynamics, we have delta Q is equal to delta U plus delta W. Therefore, for a cyclic process, delta Q is equal to delta W. As the heat absorbed and heat rejected by the system is Q1 and Q2 respectively, delta Q is equal to Q1 minus Q2. Since the work done by the system is W, we get Q1 minus Q2 is equal to W. Let this be equation 1. The efficiency of heat engine is defined as the ratio of the work done by the system to heat absorbed. Efficiency eta is equal to work done by heat absorbed, which is equal to W by Q1. But as per equation 1, W is equal to Q1 minus Q2. Therefore, eta is equal to Q1 minus Q2 by Q1, which is equal to 1 minus Q2 by Q1. Let this be equation 2. If Q2 is equal to 0, then the efficiency of the heat engine becomes 1 or 100%. This means, if we can construct a heat engine which converts the total heat it absorbed into work, then its efficiency is 100%. But in practice, it is not possible to construct a heat engine with 100% efficiency. This is not due to any technical aspect, but because of the second law of thermodynamics, which we will study in subsequent modules. There are two different types of heat engines. One type is the internal combustion heat engine. Diesel and petrol engines are examples of internal combustion engines, and the other type is the external combustion heat engine. The steam engine is an example of an external combustion engine. Let us discuss a 4-stroke petrol engine. This is also called an Otto engine, as it was first invented by Otto in 1876. The engine consists of a steel cylinder with a movable piston. The piston is connected externally to a crankshaft. There are two valves fixed at the top of the cylinder, I and E. Valve I is used to allow fuel into the cylinder, and valve E is used as an outlet of burnt gases. S is the spark plug used to produce electric sparks. The working of the petrol engine can be described in the following 4 steps. In the first step, a mixture of petrol vapor and air enters the cylinder through the inlet valve I. During this process, the piston moves down, and this is called the intake stroke. Now, both the valves I and E are closed, and the piston moves up. The upward motion of the piston compresses the mixture of fuel and air to a high pressure, resulting in an increase in the temperature of the mixture to about 500 degrees Celsius. This motion of the piston is called the compression stroke. At the end of the compression stroke, the spark plug produces a spark and ignites the fuel. The burning of the fuel generates a very high temperature and pressure and pushes the piston in the downward direction. This is known as a pass stroke, because this stroke provides a large amount of mechanical energy. Now, valve E is opened. The piston moves up and pushes the burnt gases out. This is called the exhaust stroke. In every cycle, the piston repeats all these 4 strokes. Hence, the engine is called a 4-stroke engine. Now, let us see how a steam engine works. It consists of a main cylinder with a movable piston. The piston is externally connected to a crankshaft, which in turn is connected to a flywheel. The top portion of the main cylinder has 2 ports, called the front port and back port. In a chamber adjacent to the main cylinder, a valve is allowed to slide. The sliding valve is positioned in such a way that at any given time, both the ports are either in the open state or in the closed state. At the top of the chamber, there is a steam inlet and a steam outlet through which steam is allowed to enter or leave the cylinder respectively. The flow of steam into the main cylinder is controlled by the movement of the valve. Now, let us study the working of the steam engine. Since the required steam is generated in an external furnace, this is called an external combustion engine. Steam at a very high temperature is allowed to enter the chamber through the steam inlet. Let us start with the position where the sliding valve is in front of the front port and allows steam to enter the main cylinder through it. As the steam enters the main cylinder through the front port, it pushes the piston backwards. During its backward movement, the piston pushes the used steam out through the back port. Slowly, the valve starts moving backwards and the steam in the cylinder expands and pushes the piston further backwards. As the valve moves further backwards, the steam flows into the main cylinder through the back port, and it starts pushing the piston in the forward direction. The piston pushes the exhaust gas through the front port. Again, by moving the valve forward, we are back at the initial position. The repeated movement of the piston makes the flywheel rotate. Note that the movement of the sliding valve is controlled by a separate gear system. The movement of the valve is used to control the steam that enters the main cylinder and the speed with which the piston oscillates. Now let us understand the working of a refrigerator or a heat pump. The schematic representation of a refrigerator or a heat pump is as shown. A refrigerator is a device that takes heat from a cold reservoir, and after some external work is done on it, it releases some heat to a hot reservoir. Assume that the working substance receives heat energy Q1 from a cold reservoir at a temperature T1. And after W work is done on the system, it rejects heat energy of Q2 to a hot reservoir at a temperature T2. The coefficient of performance alpha of a refrigerator is defined as the ratio of heat taken from the cold reservoir to the work done. Alpha is equal to Q1 by W. But as per the law of conservation of energy, Q2 minus Q1 is equal to W. Therefore, alpha is equal to Q1 by Q2 minus Q1. Let us understand the working of a refrigerator. The working substance in a refrigerator is called a refrigerant, and in many refrigerators, ammonia is used as the refrigerant. The main parts of a refrigerator are the compressor, expansion valve, and heat exchanging pipes. The liquid refrigerant, while passing through the heat exchange pipes located inside, absorbs heat and evaporates. The vapor, which is at a low pressure, then enters the compressor. The compressor does some work on the vapor, and as a result, the pressure and temperature of the vapor increases substantially. The high-pressure hot vapor then passes through the exchange pipes located outside and releases heat energy to the surroundings. During the process, the hot vapor condenses to liquid. Then, the liquid refrigerant passes through the expansion valve, and due to sudden expansion, it cools further. In this way, the refrigerant absorbs heat from the cooler inside regions of the refrigerator and releases it to the hotter outside regions. You have now reached the end of this module. In this module, you learned that a device that converts heat energy into mechanical energy is called a heat engine. In a heat engine, the working substance undergoes a sequence of processes that finally leave it in the same state in which it started. Such a process is called a cyclic process. In each cycle, the working substance passes through the following main processes: absorbs heat from a hot reservoir, does some work on the surroundings, rejects some heat to a cold reservoir. In a cyclic process, there is no change in the internal energy of the system. Delta U is equal to 0. The efficiency of a heat engine is defined as the ratio of the work done by the system to heat absorbed. The efficiency of a heat engine eta is equal to 1 minus Q2 by Q1. It is not possible to construct a heat engine with 100% efficiency. There are two different types of heat engines. Internal combustion heat engines. Diesel and petrol engines are examples of internal combustion engines. External combustion heat engines. A steam engine is an example of an external combustion engine. The four strokes of a petrol engine are intake stroke, compression stroke, power stroke, exhaust stroke. A refrigerator is a device that takes heat from a cold reservoir, and after some external work is done on it, it releases some heat to a hot reservoir. The coefficient of performance, alpha, of a refrigerator is defined as the ratio of heat taken from the cold reservoir to the work done. Alpha is equal to Q1 by W.